When you look up at a modern skyscraper, your brain registers a massive, immovable monolith. But if a building of that size was actually perfectly rigid, it would shatter. Deep inside its steel lattice, the structure is constantly bending, groaning, and yielding to invisible pressures. To survive, engineers use 4 strategies distributed from underground to the highest floors: center of gravity, bedrock anchors, aerodynamic twist, and tuned mass dampers. The math of a tall building is inherently precarious. You are stacking hundreds of thousands of tons of vertical mass onto a tiny patch of real estate, and then subjecting that massive surface area to lateral forces like gale force winds and seismic tremors. Look at a structure like 432 Park Avenue. Its slender, rectangular profile seems to defy gravity. To the naked eye, a tower this thin looks vulnerable to tipping over in a storm. If a structure like this relied strictly on weight and stiffness to fight the elements, the lateral strain would snap its columns. Its survival actually depends on a counterintuitive ability to yield. This vertical division diagram shows the clear distinction between a building's superstructure above ground and the substructure below it. When the surface soil is too weak to support a skyscraper, engineers have to dig deep. This diagram outlines the 6 steps to build a site-cast concrete pile. A hollow steel tube is driven deep into the earth by a massive hammer until it hits bedrock, then filled with a concrete plug and spherical base to create a permanent anchor. These anchors serve a specific physical purpose, manipulating the center of gravity. Every heavy object has a concentrated point where its mass is perfectly balanced. Gravity pulls straight down through this point. As the object tilts, it remains stable as long as that downward pull stays within its base. But the moment the center point falls outside the footprint, the object topples. These deep concrete piles grip the bedrock, locking the building's center of gravity in place. This prevents the massive structure from uprooting when pushed laterally. Moving up from the bedrock and into the structure itself, the primary defense against gravity is the central core, usually housing the elevator shafts and acting as a thick, reinforced concrete spine. To push heights past a standard skyscraper, engineers developed the buttressed core system, allowing megatall structures like the Burj Khalifa to manage unprecedented vertical weight. In a buttressed core, a central hub is supported by 3 wings extending outward. These wings act as heavy bracing mechanisms, keeping the main spine from twisting or buckling under its own pressure. When strong lateral winds push against the side of the tower, this specific Y-shaped geometry catches the force and redistributes that energy outward and down through the wings, funneling it safely into the foundation. A solid spine provides the necessary baseline stability for all that vertical mass. However, against the chaotic, unpredictable nature of high-altitude weather, remaining entirely stiff is a fatal flaw. High-altitude wind is a dynamic, swirling force. When currents slam into a flat, prismatic facade, they generate violent vortexes on the leeward side that induce severe structural bending. To break up dangerous wind patterns, engineers twist the buildings themselves. Sweden's Turning Torso Tower pioneered this aerodynamic countermeasure with a 90-degree spiraling facade. This floor plan details the structural anatomy required for a twist. The central square core remains fixed and vertical, while the circular outer columns are positioned on a slightly angled, rotating perimeter on each successive floor. This chart shows the wind drag coefficients for prismatic buildings in low turbulence. The math proves that by rotating the outer frame, the structure significantly reduces overall lateral wind loads compared to a standard model. Twisting the building's skin actively scrambles the wind's physics, shedding vortexes and reducing overturning momentum before it can threaten the frame. Even with deep bedrock anchors, a rigid core, and aerodynamic twisting, typhoons and extreme weather events will inevitably cause the top floors of a tall skyscraper to sway. To prevent that swaying from becoming dangerous or making the occupants sick, engineers install an active defense mechanism known as a tuned mass damper. A tuned mass damper relies on the physics of inertia. By suspending a massive, heavy weight from springs near the top of the tower, the mass naturally resists changes in motion. When a gust of wind pushes the building in one direction, the free-hanging mass lags behind, effectively pulling the building back. The system has to be precisely calibrated. The swinging frequency of the mass must perfectly match the natural swaying frequency of the building itself. every time the tower shifts right, the pendulum swings left in exact opposition, canceling out the motion. The structure survives a direct hit by allowing the initial movement to happen and then instantly neutralizing it with an equal and opposite mechanical punch. Zooming out to the skyline, it becomes clear that a surviving skyscraper operates as a holistic system. The gripping roots, the braced spine, the aerodynamic skin, and the heavy pulsing heart all work in concert. Absolute stillness at this scale is a structural impossibility. To avoid being broken by nature, a tall building has to yield to it. These towers are highly tuned, flexible machines, performing a continuous, invisible dance with the forces of the earth just to stay standing.